So today I'll be talking about a fundamental problem in mathematics, and that is to study the maximum number of one entries in a 0-1 matrix that avoids certain patterns. So this problem arose from computational and discrete geometry around the 1990s, and it has applications to mathematics in the Stanley-Wolf conjecture, in graph theory, and in computational and discrete geometry, to engineering in robot motion planning and circuit design, and to computer science in algorithmic complexity. So the key concept here is pattern avoidance for 0-1 matrices. So we say matrix A contains matrix P if some submatrix of A can be transformed to P by changing any number of ones to zeros. So in this example here, we can find a green submatrix in which we can change the bottom right 1 to a 0 to get an exact copy of the right matrix. So we say the left matrix contains the right matrix. And we say A avoids P if A does not contain P. So we use this standard notation here to denote a D-dimensional matrix A, where D is the number of sub-indices. And in general, we can view a two-dimensional matrix, 0-1 matrix, as a rectangular table of entries, and we can view a D-dimensional 0-1 matrix as a D-dimensional rectangular box of lattice points, each labeled with a 0 or a 1. So in the picture, the three-dimensional matrix on the left contains the three-dimensional matrix on the right. So the main object of interest in our talk today is the extremal function, denoted by f, which is the maximum number of ones in a D-dimensional matrix of this size that avoids the D-dimensional matrix P. So as an easy example, if P is a row of 5 ones, then an n by n by n matrix that avoids P has at most 4 ones in each row, so it has at most 4n squared ones total. So the extremal function is 4n squared. So in general, it's actually not practical to calculate the extremal function exactly. Instead, we'll be estimating it. So now a cross-section of a D-dimensional matrix is just a set of all entries which share one coordinate. So in this example, all the entries of the same color represent a cross-section. Now we can prove some trivial bounds on the extremal function. So if P is any non-trivial D-dimensional matrix, then the extremal function is always between n to the d minus 1 and n to the d. So the proof of this is quite simple. For the upper bound, just note that any D-dimensional matrix has at most n to the d 1 entries. And for the lower bound, we can choose a D-dimensional matrix with 1 entries or on a single cross-section and zeros everywhere else that avoids P. And this matrix has n to the d minus 1 1 entries, so the extremal function, we get a lower bound of n to the d minus 1. So given these two trivial bounds, our main goal in this talk is to improve the trivial ones of n to the d minus 1 and n to the d on the extremal function so that their orders are as close as possible. So now I will describe the two most important 0-1 matrices. The first is the permutation matrix, which is a 0-1 matrix in which each cross-section has exactly one entry. So in the picture, this matrix is an example of a three-dimensional permutation matrix. And then the second type is the tuple permutation matrix, which is obtained from a permutation matrix by replacing each 1 with a row of 1s and each 0 with a row of zeros of the same length. So in this example, we start with the permutation matrix on the left and replace each 1 with 2 1s and each 0 with 2 zeros to get the tuple permutation matrix on the right. So now I'll briefly describe the asymptotics notation that I use in my results. The first, big O, means f grows at most as fast as g. The second, big omega, means f grows at least as fast as g. And the third, big theta, means f grows as fast as g. So my first main result is about a type bound for tuple permutation matrices. So a type bound, denoted by the big thetas shown here, just means the lower and upper bounds have the same order. So previously, tight linear bounds were found for two-dimensional permutations and two-dimensional tuple permutation matrices. And a type bound n to the d minus 1 was found for d-dimensional permutation matrices. And I generalized these past three results by showing a type-bound n to the d-1 for any d-dimensional tuple permutation matrix. The significance of this result lies in the fact that since n to the d-1 is a trivial lower bound, type-bound n to the d-1 is the lowest possible order that a non-trivial extremal function can have. So for the proof, just note that since n to the d-1 is a trivial lower bound, we just have to show the upper bound big O of n to the d-1. Then we use some combinatorics to derive a recursive inequality on the extremal function, the resolution of which gives this upper bound. So now I will be discussing d-dimensional matrices P for which we have this type bound on the extremal function. And as we saw on the last slide, this includes d-dimensional permutation and tuple permutation matrices. So since we have this type bound on the extremal function, the sequence f over n to the d-1 is a bounded sequence. And the main question we're interested in is whether this sequence converges. So the answer is yes for 2 dimensions, and the proof used the superadditivity of the extremal function and Feket's lemma to show it converges. However, it's still an open problem to show the sequence converges for higher dimensions, but here's my attempt to prove this result for d greater than 2. So we first observed that for 2 dimensions, superadditivity implies superhomogeneity, and we conjectured that superhomogeneity of a higher degree prevails in higher dimensions. And what's important is that we can modify Feket's lemma to show that this form of superhomogeneity implies the sequence converges. So I discovered this idea of superhomogeneity at the Research Science Institute this past summer, but I'm only able to prove it for a few special matrices P. But when I got back from RSI this past summer, I saw that this weaker form of superhomogeneity, which we can prove for a much larger class of matrices P, is also vital to pattern avoidance of multidimensional matrices. And we'll see why it's important later. So since the convergence of the sequence is an open problem, we instead consider the limit superior and the limit inferior. So since the inferior is always less than or equal to the superior, we'll be showing upper bounds on the superior and lower bounds on the inferior. So my second main result deals with an upper bound on the superior. So we let k be the size of P. Then previously, upper bound 2 to the big O of k log k was found for 2-dimensional permutations, d-dimensional permutations, and 2-dimensional tuple permutation matrices. But the real breakthrough for studying this limit was when Fox showed an upper bound of 2 to the big O of k for 2-dimensional permutation matrices. And the first part is that I generalized this to d dimensions, and I also showed the same upper bound holds true for d-dimensional tuple permutation matrices, which is a near result even for d equals 2. So for the proof of these two theorems, the key ideas were interval minors and using a recursive inequality. So my last main result is about lower bounds on the inferior. So it's not hard to prove that the limit inferior is at least linear in K for any d-dimensional permutation matrix P, and that this linear lower bound is actually achieved by the d-dimensional identity matrix. So it's a natural question to ask how large the limit inferior can be for some permutations P. And we answer this question in this theorem by showing that the limit inferior can be at least exponential in K for a family of d-dimensional permutation matrices. So Fox was the one who showed this was true for 2 dimensions, and we showed it was true for any number of dimensions. However, our proof is significantly different from Fox's, and I will outline it here. So the first step is showing the weaker form of superhomogeneity that I mentioned earlier holds true for every matrix P with a corner 1 entry. Then we can use this equation to prove a Feket-like lemma, which gives a lower bound on the limit inferior. And then the third step is showing a probabilistic lemma similar to the one that Fox used in his proof. And then finally, we can simply choose M to be capital N in here to show this bound on the limit inferior. And that concludes the proof of this theorem. So what's nice about all the results that I talked about today? Well, we generalized major results in 2 dimensions to higher dimensions, and in the process, we discovered many new ideas, such as superhomogeneity of the extremal function, which are vital to pattern avoidance and multidimensional matrices. Additionally, our work has a direct application to hypergraphs, and it may have applications to other areas of math, such as computational geometry, computer science, or engineering. So in the future, one possible direction is proving the stronger form of superhomogeneity, since this will imply the convergence of the sequence. A second possible direction is improving our result on the limit inferior lower bound by getting rid of the corner one entry condition. And the last possible direction is improving our bounds on the limit inferior and limit superior by getting tight exponential bounds on them. So finally, I'd like to thank my mentor, Geneson of MIT, for his constant and patient support, Professor Chumatov of The Ohio State University for his continuous support throughout my high school years, Professor Eddinghoff, Professor Fox, Professor Geneson, and Dr. Kovanova of MIT for their many helpful comments and suggestions, Primes USA, RSI, and the Department of Defense for supporting this research, and finally, Siemens Foundation, Discovery Education, and George Washington University for having me here today. So here are my references, and thanks for listening.